time for getting spin. One state could correspond to some particular wave. It doesn't have to be an atom, incidentally. It could just be any system. But let's take some of these atomic states here. Okay. This wave function, or the wave function associated with this state here, could be called size 0, let's call it. 0 because it has 0 angular momentum and because it's the lowest energy state. All right, so we're going to put particle 1 into that state. So the wave function for particle 1 would be size 0 of x1. Let's put the next particle in some other state. It could have the same angular momentum or a different angular momentum, but let's make it a different state. Let's make it a different state. So, let's first do the case where we put the particles into the same state. So, let's put two particles into the same state. Then the state vector would be size 0 of x2. Particle 1 in the state size 0, particle 2 in the state size 0. Does this satisfy the rule for fermions? Does it satisfy the rule for bosons? Well, this structure here is obviously unchanged if you interchange 1 and 2. It doesn't matter which order you multiply wave functions. Wave functions are just have numerical values. They're not operators, they commute. Okay, so this wave function here, two particles in the same state, that's symmetric. The word is symmetric. Symmetric under interchange of the two arguments of the wave function. It does not change sign. So that if such a wave function makes any sense, it makes sense only for bosons. For fermions, this is not possible because this does not satisfy the rule for fermions. Okay, let's try another state. And another way of saying it is you can only put bosons into the same state. Put bosons into the same state. Okay, let's take one particle and put it into size 0, and the other particle put it into another state which I'll call psi 1. Okay. What happens if I interchange 1 and 2? Not 0 and 1, but what happens if I interchange x1 and x2? This will become psi 0 of x2, psi 1 of x1. In general, if these are two different wave functions, the left side and the right side will neither be equal to each other nor equal to their negative. Just product of two functions. Sine of x1 times hyperbolic mousse of x2. That has no symmetry whatever. It doesn't change sign or it doesn't stay the same. So this is not a possible wave function for either fermions or bosons. Does that mean you can't put one particle into one state and another particle into another state? Not quite. Let me now take a state which is made by taking both of these combinations here and adding them. This is a wave function, perfectly good wave function. It's a superposition of particle 1 being in size 0, particle 2 being in psi 1, and the opposite, particle 2 being in psi. But both of them have a particle in size 0 and a particle in psi 1. They both satisfy the criteria that there's a particle in psi 1 and a particle in psi 2. So both states have been filled. But what about this? What happens to this if I interchange 1 and 2? Nothing. It stays the same. Okay? So this is a perfectly good candidate for a boson system. Two particles in the same... No. A particle in state 1, in state 0, and a particle in state 1. Here's how you build it. What about fermions? Can you create a state with a fermion in this state? in this state? Yes. All you have to do is put a minus sign there. Okay, can you check? Does that change sign when you interchange X1 and X2? Sure it does. This one goes over to here, this one goes over to here, the whole thing just changes sign. So yes, you can put, in both cases, you can put a particle into state 1 and a particle into state 0. What you can't do for fermions is put two particles in the same state and two particles, or for bosons you can. Okay. In particular, let's take the special case of exactly this, where psi 1 and psi 0 are the same state. It's just a special case in which, instead of taking two different states, I take the same state. Okay, so two possibilities, psi 0 of x1, psi 1 of x2, plus psi 0 of x2, psi 1 of x1. Boson, fermion wave function. Now let's take the cases I said where both wave functions are the same. Well, this just gives me twice the original wave function. Alright, it may not be normalized correctly, we may have to normalize it appropriately, but it gives us twice the original wave function and it's not zero. Nothing wrong with it. Again, it's two bosons in the same state. Perfectly good. But the fermionic construction here gives us what? Zero. So again, we can't make a state in which two fermions are in the same state. The same rule continues if you have multi-particle states. If you have multi-particle states, any number of particles, then the wave function is a function of many variables.
This expansion is the right time obtained from setting.
And it has the property that for bosons, if you take any two of them and switch them, the wave function does not change sign. For fermions, if you take any two of them and switch them, it does change sign. Again, what happens if you switch twice so that you come back to the same configuration? Clearly, in both cases, nothing happens. Right? So the process of double swap is nothing at all. It's trivial. It doesn't do anything, as you would expect. As you would expect.